All right, so 13.2 is on what we call vector valued functions. Okay, and so this is really nothing new. You've seen everything that you talk about as a vector valued function, you could just think of as a parametrically defined function instead. It's just a different way to write things out. So when we say something's a vector valued function, right now we're just going to have one variable. You could even have vector valued functions of two variables. But the idea is just, right, that you have some formula for what your x component is doing. So you have a function times your x. So this is where you are in the x world, plus you have another function times the j. Does that make sense? And then a third function, a third function times k. If you're in three-dimensional space, you might also just talk about this in two-dimensional space. We'll just drop off the k's terms there. And so again, this could also be represented like this: f of t, g of t, k of t. Okay? And so, you know, it looks kind of cumbersome and ugly, but just keep in mind this is exactly what you were doing with parametric functions, right? You were just saying x's follow some function of t, y's follow some function of t, z's follow some function of t. That's really all it is. It's just a compact way to write out parametric functions. So let's try sketching a couple things here. Some of this gets really hard to draw, and so don't be too intimidated. I'm not going to expect a lot of beautiful artwork out of you. All right, let's just start in 2 dimensions here. We'll start with a really basic one, and let's do 0 less than or equal to t less than or equal to, we'll go to pi. All right, so think about this in terms of, like I said, parametric functions. So your x's are sine, your y is cosine. And so when you try to sketch these things, I'm really just going to do this as though it's a parametric equation. And so the idea there was that you could eliminate a variable, you could get rid of the t, and try to sketch it from there. So think for just a second if you can sketch it out. We'll do it together in a minute. So again, if you didn't see this, or this looks familiar, don't get too worried about it. The point was that x was going to act like sine of t, y is going to behave like cosine of t. You're going to see this same thing happen over and over again, so get used to this. But don't be too worried if you didn't follow it. So what equation do these x and y satisfy that you're used to? Well, again, you could have thought about it for a little while. Well, what's x squared plus y squared? If x is sine, y is cosine.
R squared.
Well, not just r squared, but just 1, right? There's no r in there, but that's just 1. Does that make sense? So what's x squared plus y squared equals 1? What's the graph of that? Circle, radius 1. So what we know is that this vector valued function sits on the circle of radius 1. We don't know which piece of it, right? It might be all of it, it might be just a portion of it. But since it satisfies this, we know it's at least stuck on that circle. Does that make sense? So now let's figure out which piece of that circle we're on. So what's r of 0? If I plug 0 into my vector valued function, I get sine of 0, right? And then cosine of 0. So 1, so that means we're starting up x is 0, y is 1, right? What's r of pi?
0 negative 1.
Yeah. Sine of 0, sine or cosine of, sorry, sine of pi, cosine of pi. So sine of pi is also 0, cosine of pi is negative 1, so we're down here, right? So we started up here and we ended up down here. So how did we get there? Did we go this way? Did we go that way? Did we wrap around a couple times and end up back there? Okay, so like this. Well, that's correct, but how do you know that? So this is the correct piece, but how do we know that for sure?
Because we're going from the minimum to the max.
Well, but I mean, you still would go from there to there if you went that direction, right?
Are we using
Science pi half.
Okay, so there would be one way to look at it, would be to take a midpoint and just see where you're at, right? If you put pi over 2 in, sine of pi over 2 is 1, cosine of pi over 2 is 0. So that means you ended up at this point, right? Another way to think about this is that if sine is here, if sine is 0, and then sine goes to pi, what does sine do? Sine starts at 0, and then as t grows, it goes up, right? So your sine's going to go up. So your x values are going to increase, which means you're going to go to the right. Does that make sense? So that's sort of the ideal way to think about it, is not just grabbing a point. Because you could have something that, whips around 50 times, and even though you grabbed what you thought was a middle point, it was because you went this way and got to there, and then you made it back there. So you got to be careful. I mean, in practice, they're all pretty straightforward. But theoretically, all kinds of really crazy stuff could happen. All right, let's look at another. Very similar idea. We'll stick in 2 dimensions still. What if I have 2, let's do cosine of t this time. Cosine of t and then negative 3 sine of t. All right, now I want you to think in that same way we were on the last one. Sine squared plus cosine squared is 1, right? So you don't have just sine and cosine. You got 3 and a 2 in front of them. But you force your equation to look like sine squared plus cosine squared. So how can we do that? If I want cosine squared, I can't just square x, but I could square x over 2, right? Does that make sense? If I take x divided by 2, now I got cosine, and I square it. And then I can do what with the sine, or the y? Y over 3, we're squaring it, so I don't care that it was negative 3, right? I just get that, and that should be 1. Does that make sense? So just to be clear, that's cosine, and that's negative sine, right? When we divide it by those things. And so we square them, we get that. So now, this is x squared over 4 plus y squared over 9 equals 1. What kind of? Well, not a semicircle, but an ellipse, right?
Yeah.
I think that's what you meant. So it's an ellipse, and then what are the intercepts? So if y is 0, right? So now y is 0, you're on the x-axis. That's gone. What's x?
2.
2 or negative 2, right? And then if the x is gone, so you're on the y-axis, what are your y's?
3 and negative 3.
3 and negative 3. So you get an ellipse like this, right? And again, I don't care about how, oops. So, negative 2 to 2, I'm going to exaggerate so we see that it's an ellipse. Again, your picture doesn't need to be perfect, you just should get that idea that it's some kind of oval shape, right? All right, same idea now, but which part of this curve do you go around? Oh, I didn't give bounds here. Let's do the same kind of bounds. 0 less than or equal to t less than or equal to pi. So figure out, so again, satisfies this equation so you know you're on this piece of the ellipse, or you're on a piece of the ellipse. Figure out which piece you're on. So let's just do that. In particular, you at least need to figure out r of 0 and r of pi, right? What's r of 0? 2, 0,
Yeah.
right? And what's r of pi? Negative 2, 0, right? Just sine and cosine of pi, plug them in. Okay, so that means you're starting off here, right? And then you're ending there. Is that okay? So now, top or bottom, which part did we go across?
The fourth quadrant?
Yeah, so you could check at pi over 2 if nothing else. If you have,
Or not the fourth.
no, that's right, it's gonna come down this way, right?
Yeah,
Fourth quadrant,
okay, yeah.
and then go up through the third as well. But if you take this one, you'll get 0, negative 3, right?
Okay.
And the other way to think of it is now my sign is negative, right? And my sign is now my y values. And so if the t starts at 0 and grows, negative sign is going to go negative, right? So I'm going to go down. And so we're going to take this piece of it. And if you have a calculator and you set it to, parametric mode, I guess it does vector valued functions too. It should, well, actually that's not true. Depends how nice your calculator is. If you have a really crappy old calculator like I have, you see it slowly trace things out, and so you see the direction it goes. The new calculators just pop up the answer. So another reason to invest in an old crappy calculator. Okay, let's do this next. Everybody have this written down. I'm going to put up something on the screen, so let me know when you're ready to pull the screen down. Oh, actually, let's do one more before that. I'll come back. This will work out well. So R of t. Okay, so now I have a vector valued function in 3 dimensions. I'm not going to put bounds on this one. Let's do bounds just t greater than 0. T greater than or equal to 0. All right. So things get a little bit uglier here, but hopefully not too bad. Notice, right, x, y, and z are like this, right? So as t grows, let's ignore the x and the y for a second. What's z going to do? If z is just t, and t grows, you're just going to grow, right? So whatever your points do, your z values are just going to keep going up. Does that make sense? And then what are your x and y going to do? Well, just like our previous problems, they're going to satisfy this, right? And so in 2-dimensional space, where does this guy start? T equals 0, 0, 1, right? So you're going to start up here at 1, and then you're going to go like this, right? And now this time I don't have bounds, and so I'm just going to keep wrapping around this circle, right? So my x and y values are going to keep spinning around a circle, and my z values are going to just grow. And so what's that graph look like? You have the right shape, right? It's just going to spiral up. Does that make sense? So you want to start in the right place. So you start at y. So remember, x, yz, right? And we start at y equals 1, x equals 0, so we're going to start here. And our z values are just going to grow. And again, this is a place where I'm not expecting you to be some great artist, but if you looked down on it, it just looks like this, right? But your z values grow, and so you want to demonstrate somehow that you're spiraling out. So you're going to end up, or you probably should, I should think about these before I try to draw them again. Right, so just show some indication that you realize you're going up, right? So you don't have to be perfect, but just make sure you show I'm crossing in front of that guy, right? In front of those things. Something along those lines. And this looks like I'm touching, I don't want that to touch. I'm going to be above that. And if you need to, you can put in some extra values to show what's happening, but we just, all we're ever going to really need is just that feel for what that thing looks like, right? Look like a spring kind of spiraling away. Okay, so let's do this next. So rather than try to draw a bunch here, I just want us to try to match these functions up. So this is 1 through 6, and I want to match them up with the vector value function given down here, 25 through 30. And so it's hard to see them all at once. So I'm going to write the 25 through 30 on the board next to these, and then I just want us to try to match them up with the right math. So if you can do that, if that's one of the takeaways from today, even if you're not able to really sketch them nicely, that's probably more valuable than anything right now. You can see what those sketches should look like. So again, I'll write the functions up here and then we'll try to match them up. So 25 is t sine of t, t cosine of t. If it doesn't give bounds, which I don't think any of them do, you should just assume you start at 0 and then you go from there. Okay. So take a minute, see if you can guess which ones match up with what. You don't have to be perfect. Just see if you can somehow get a piece of it. If nothing else, just pick 2 of them and think about, okay, well, how are the x and the y acting with each other? How are the y and the z, or something like that? And then you should be able to extrapolate from there. And I guess I should also point out, hopefully it's pretty clear that the things that spiral or loop are the things that are going to have sines and cosines in them, right? Because those are periodic functions. And the things that look like they just keep going on forever in directions are the things that won't have the periodic. So these 3 in the bottom are going to match up with those 3, and then these 3 will match up with the ones that have sines and cosines. So think about it for a minute or so, and then we'll try to answer them together. So I'm just going to write next to here, I'll write the corresponding guys. All right, any thoughts? Any one of them that you think you know?
25, 5.
25, 5? Yeah, so 25 and 26 are pretty close to each other, right? They both have a t in them. And so the t is showing up in the x component, right? So as t grows, that x should spring up. So 25 and 5 is not a bad guess, right? It's coming out that way. But what's the difference between 1 and 5 up there? They both have your x values coming out, right?
But y is increasing.
Well, both, so x comes out, and then y and z are both just kind of spiraling around in both of them, right? But which one, so I guess 25 is not 5, it's actually 1. 26 will be 5, but how do you know that?
Could we just move there?
Oh, is it because z, it looks like z's constant at 1?
Well, right,
Or
so,
it's
so,
constant at that 3?
yeah, so the first one, right, what are you at when t is 0? Where's the first one? It's starting right at the origin, right?
Yeah.
And so if you look at 25, that works out perfect, right? Because you got a t times sine and a t times cosine. And so this one, right, your sine and cosine are gonna flip between -1 and 1, right? They're gonna oscillate. So you're gonna move around like this, but you're also multiplying them by t. And so you're not only doing a circle, but it's an expanding circle, right, as you move out. And so that one corresponds with 25. Now what do we say this one was, 5? And so it's kind of a cheat, but then that gives you, which one here? 3. And let's not worry about all the details, but look at this one, right? Sine and cosine are going to behave just like they did up here, right? So your x and y, or your y and z are going to spin around, but then you also have your x values are going to be bounded. And so your y and z are going to spin and your x will spin, and so you're going to be stuck on that circle. Exactly why we're not showing, but hopefully that makes sense. Okay? All right, how about these other ones? So look at this one. T squared, t squared, t squared.
3? No.
4? Yeah, I think it's 4, right? Because now as t grows, x, y, and z all grow at the exact same speed, right? And so you just kind of go up through the middle of that thing. So this guy's 4. How about the other two?
You want the one?
6.
Okay, so 2 should correspond, oh, I put it in the wrong place. Thank you. Is that what you guys were saying?
Yes.
29. Okay, so 30 and 28. Which one's 28? 6? I think that's right. Why?
Because z equals to y.
Okay, so
Whereas the
so that means this one looks like here's y, here's z, right? And so y equals z is true, right? And so whatever your points are, they're going to satisfy that. And this looks like you're on that line, right? Y equals z, and then your x values just change. So I think that's right. So this one should be 6. And then that leaves us with the other one, and you can kind of make the same reasoning there, right? This time, x and y are the same, and your z's just grow. And this one's a little bit harder to see, but I think you're on that line, y equals x, and then your z's are just growing. So this one is 2. Does that make sense? So, I know this was assigned as part of your homework, but I think it's a good exercise to come back to after you've taken a few hours and have thought about it, and try this one again, be able to match those things up. I think we're probably out of time. Let's just stop there. Yeah.